All right, well, our second speaker and our last speaker for the conference is Jean-Marc Jomard.
Thank you. So what I will explain today is some more ideas on what may be an effect of the zigzag instability. And this will be, the first part of the talk will be on the dynamic of shear layers when the shear is horizontal and the velocity is horizontal for that. And I will build on that the dynamics of stratified flows. So first I want to acknowledge my collaborator on that. So Ramiro, Paul, who is my long-time collaborator, and many ideas goes back to Paul in that talk, and Axel, who did his PhD very recently last year with us, with Paul and me. So since I'm the last talks, I say, okay, I will try to thank formally the organizers. So first the staff, and I must say I have a great thanks to this to the organizing structure, because they have been very efficient, mixing all the ideas of the community, even if there is more big fishes in the room that have also participated in the mixing. I don't know which one was the most efficient for that. And now what I will try to explain today is I will go back to more serious dynamics of vortices. And when you look at more serious dynamics of vortices in stratified flows, the question I want to ask is what will be the scale that will take all these big vortices. So what will be the vertical scale selected by the flow? I thought at one point to use Michael pictures to do that, but I say no, if I got plenty of Michael's pictures or Michael's in the room, then it will be a disaster. But Michael is not he's not listening. So the question is, what will govern this vertical scale, and what we can say about the dynamics of stratified flow, and about, in particular, the scaling laws or the balance that will define this vertical scale. So this is my last jokes. Maybe there is me. I don't think there is more jokes in that for that. So what we are very busy. So after that, I start with a very busy slice. Is that what we may do if we want to understand the dynamics of stratified flows? So these ideas go back to Jim somewhere. It should be on the slide. Maybe it will be on the next one. So to Jim Riley, Metcalfe, and Weissman. So what you have to do is you want to look at the dynamics of vortices. So you have to take the scaling for the vortices, so a particular velocity u, a particular scale, horizontal scale LH, and a particular time scale that will be the time scale of the vortices. And what you will do, you will look at the limit where the vortices are slow compared to the gravity waves. So this is the limit you want to take. And maybe you will take a limit where the Reynolds number will be large. And then you just go through the dominant balance of the flow. So the dominant balance of the flow, the pressure will be given by the 2D dynamics. So this is the horizontal transport. So this is the convective dynamics, the convective derivative with the horizontal velocity. So the pressure is given by this balance. The density is given by the balance of the pressure. So the density is forced by the fact that it should balance the pressure gradient. And then the vertical velocity will have to balance the variation. It will be forced by the variation of the density, like that. And this is what you may say. And now if I let the vertical scale unspecified, after that you have the choice for the different terms. So this term will have this particular scaling involving the Froude number, and the viscous term, the dominant term of the viscous term, will have another scaling. It will be proportional to 1 over Reynolds number aspect ratio to the power 2, like that. And the key ideas that I will try to explain in that talk is that there is a very simple thing to remark, is that we have a choice to know what will be the dynamics of the flow. We may either think this term will win over that term, and this will be given when the Reynolds number Froude number square will be at a particular value. So I will develop that idea in the rest. In fact, it was just when I click, I forgot. So the dominant thing to remember is that we have a choice for the physics of the flow, and it's all depend on the value of this parameter for the flow. So let's start first by even simpler ideas. is that now let's take the limit Jim took a long time ago. If you say that the vertical scale, let's say that the vertical scale is about the same as the horizontal scale. So what you will get in the equation, all the white part, this was a big job to do that. So all the white part have erased all the terms that are negligible, and this is the leading order dynamics. And this dynamics is very simple. It's just the Euler equation parameterized by the vertical scale. So there is no coupling on the vertical scale. So all the layers will live their own life for that. And there is a very easy physical interpretation of that, is that if you assume, in this limit, you assume that the vertical scale is large compared to the buoyancy length scale. The buoyancy length scale is when you convert all the kinetic energy into potential energy for one particle. So this may be viewed as kind of an upper bound, not as smart as the previous speaker upper bound, but just an upper bound for the deformation of any isopycnol. So if you assume the vertical scale to be large compared to this deformation of the isopycnol, at leading order, the isopycnol will be flat. And what you have to do is you have to conserve potential vorticity, but the isopycnol are flat. So there is no stretching, so this is just the vertical component of the vorticity. And you have to conserve the mass, and you end up with the Euler equation. So this is the same result at that result, but just with hand waving argument for that. And this is the basic physics, but this is a very important physics, because if you imagine now any particular flow, so this I'm taking here an horizontal shear flow like that. So it varies on the vertical, but if the fluid number is small, you will imagine that at leading order, if you take any variation of any scale that is large compared to the buoyancy length scale on the vertical, all these mixing layers will behave independently, so they may all roll up in an independent fashion. So you will have the fact that any of this, any variation, vertical variation of this roll-up of mixing layers will have the same growth rate. So the particular point is that now if you take a vertical wave number that is small enough for that in the flow, the growth rate of this vertical wave number will be as large as the 2D growth rate for that. And this will be true for the linear evolution, and this is also true from the nonlinear evolution of the flow for both. So what are the other limits you may take? You may take another limit saying that, and this is a natural thing when you learn at school or to do asymptotic expansion. Let's imagine that you have a free parameter. Let's say that there is nothing that specifies the vertical scale of the flow. So you don't take into account the size of the fishes. And you say, okay, the vertical scale of the flow is free. And what you have to do, you have to take the dominant balance, and you have to bring as many terms in this equation at the same order as the leading order term. So what you have to do, for example, if this parameter Reynolds number, Froude number square is large, the largest term in this equation compared to the diffusion, vertical diffusion, is this term, and you will have to bring it to order 1. So you have to take a balance where alpha will be just the Froude number. So what is the natural balance of the flow is that the vertical scale should adjust to the buoyancy length scale. So this is work with Paul some time ago to just say that, but this has a very particular implication. So what is the balance? The zigzag, we call that the zigzag balance. I don't know if there is a name. But let's say it's the same as the zigzag instability balance, is that the equation in that regime should, so the vertical scale will be the buoyancy length scale, and the equation in that regime will be this set of equations with a vertical coupling between layers that will be due to the vertical transport. So vertical transport will transport the mass, and it will also transport or stretch the potential vorticity. And this is the physics of the zigzag, all the zigzag instabilities. So what is the other limit of the flow? Now you may have this parameter that is small, and I recall that this parameter may be small even if the Reynolds number is large. You just have to take a Froude number small enough. So this may be a large Reynolds number flow, but still with this buoyancy Reynolds number. So this is the buoyancy Reynolds number, I forgot to tell. And in that limit, what you have to do is to take the other dominant balance. That will be the aspect ratio of the flow will be given by the square root of the Reynolds number. So this is a very natural balance. And then the equation will look like that. And in this equation, the density fluctuation are just slave to the horizontal equation because there is no vertical transport. So this will give you rho, this will give you the vertical velocity, but there is no coupling. Yes? Is it the what? Except that you keep the vertical transport. So this is, you keep the vertical transport continuously in Z. For that. So, so that is the other limit of the flow that you may, the other dynamics of the flow that you may get. And that has been used also by Pro and Fincham to compare with some experiment done in Grenoble for that. So now let's take the stability. Let's look at the stability of an horizontal shear flow. So let's take the usual hyperbolic tangent profile. And what I will do, I will look at what is the stability of that flow when the fluid number will be small. And I take the case where it will be inviscid, so the Reynolds number is infinite in that case. So let's take that simple flow, and let's do the usual stability analysis perturbing the base flow with a particular wave that will depend on x and z. So if you do that, first, if you take the case that is homogeneous, the homogeneous case, what you have to solve is the Rayleigh equation for the vertical velocity, and there is a very well-known transformation. So first, if you look at the 2D instability of that flow, so this is well-known, you have the shear instability that will select a particular wavelength around 0.5 here. But if you look now at 3D perturbation, so you allow kz to be different from 0. So this is this graphic with kx and kz. What you have a simple transformation on that equation that will tells you that the growth rate of any 3D perturbation will be equal to the growth rate of a 2D perturbation with the modulus of k as the kx value for the kx times kx divided by k. So this will be smaller than that quantity, but from the knowledge of this curve on the kx axis, you may draw the ball curve on the kx, kz axis. In particular, the neutral point that is at k x equal 1 here will be transformed into a circle that is the neutral circle of the flow. So inside this circle of radius unity in kx and kz, the flow is unstable on that side and stable on that side. So this is the dynamics of the usual Kelvin-Helmholtz instability. So it's isotropic in a way that the size of the unstable domain in the kx and kz plane is inside the circle, like that. Of course, it's preferred to be a 2D instability, but many over kz, but in a small range of value of kz, will be unstable with a similar growth rate. So now let's take the case of the stratified flow. So this is the work of Axel DeLong. So then you have a little more complex equation where you just replace k in that equation by k tilde that will take into account the stratification here for that. And what is the end result of that is that if we just compare the stability of fluid number 1 and fluid number 0.05, what you will have is that you have the domain of instability that if you compute it for the small fluid number, what you have to notice is that the shape is about the same and is not too different from the 2D flow, except that the scale on the vertical, so the number of the kz that has been destabilized by the fact that you stratified the flow has increased a lot. So this value of 1 has been multiplied by this exactly the 1 over the fluid number. So you have destabilized all the kz wave number up to a very large value that is proportional to the inverse of the fluid number. And this is very important because this means that in the flow, there is a huge range of wave number, 3D wave number, that are as unstable as the 2D one. So this will weaken the 2D selectivity of the Kelvin-Helmholtz instability. So we may see that if we take just a value, so this is just a cross-cut of the previous curve. If I cut this curve, at the maximum, if I look at a cut of that curve to compare the different flume number. So this is what I'm doing on the next slide. I will obtain the variation with the flume number. So this is the cross-cut just for this particular value, the maximum value for kx, versus the vertical wave number for flume number 1, flume number 0.1, etc. And if you rescale by the flume number, the kz by the flume number, which is what is predicted by the zigzag balance, then you will obtain that all the curve will collapse. So even at flume number 1, you have already in the very stratified regime for the linear stability of the flow. And the message is this one. I already told you that for that. So now what is nice and why we start doing that is we start doing that flow because I was visiting San Diego, and Sarkar was doing with his student Bazak the stability analysis of the mixing layer, exactly the same dynamics, but just from the pure DNS. And this is the results of the DNS. So this is for particularly value of the flume number. And when he was computing the evolution of the 2D mixing layer, horizontal mixing layer that will vary on the vertical, any single slice, horizontal slice of the flow will show you a dynamics that looks like the 2D dynamics of the flow. So this is exactly what you will observe if you were doing just 2D dynamics of the flow. But if you are looking from the cross-cut in the middle of that flow and you look on the vertical, so this is the vertical, you observe that the flow has selected a particular length scale here. And the question is maybe still open to know if this is the buoyancy length scale, because all the simulation people are trying to do maybe two small flume number for the Reynolds number and the resolution they are ready to afford. So maybe the Reynolds is not sure that they are strictly in this inviscid regime. But what I want you to observe in that, and we will see it on the next slide, is that this flow is also generating very small scales here, kind of dislocations between different layers. And we may also observe that in the next slide. So this is also for the same paper. This is the vertical vorticity. So we observe this maybe thick pancake vortices. But when we observe at the horizontal vorticity, we observe very thin layers. And those are what the crepe that Yoshi has been observing in his simulation. So this is the French pancake, this is the American pancake. And the question is that now the question is that maybe the American pancake are on the zigzag type of balance, and could it be possible that this French pancake be on this viscous balance? Sorry? Crepe, yes, crepe. And Paul is from Brittany. I must say Paul is from Brittany, and so Brittany is the place where they cook crepe all the time. So in fact, we got the same observation before doing this simulation. We got the same observation when we were trying to look at the dynamics of a particular pancake, and the idea was to select the size of the pancake, so to impose a vertical scale on the flow by what Yoshi called the guillotine. So we were just calling that a screen, but Yoshi was visiting us and he said, okay, this is the guillotine experiment. We have not been respectful to our king in France and for that. So what is this experiment? It's the experiment where we did this zigzag instability. So this is a 2D flap, I mean a vertical flap. You will close the flap as if you were closing a very big open book. So this will expel the fluid, creating a dipole like that. And to obtain a particular pancake dipole, you just put this guillotine that is a screen with one particular opening. And then the flow will go through that screen, and you will produce a dipole with a particular vertical scale. So the observation here would be done by a PIV with a laser sheet and a CCD camera on that. So this is a view of the experiment, real view of the experiment. So this is with dye visualization. The guillotine is here. The dipole went through here, the guillotine, and the rest of the fluid has been stuck behind the screen here for that. So what do we observe in that flow? And this was a surprise for us. We were just trying to observe maybe the viscous regime and the way the vortex were diffusing. But when you are creating very tall vortices, what you do observe, so this is the initial time, this is subsequent time, this is the modulus of the velocity, this is the modulus of the, not the modulus, the vertical vorticity in the flow, I'm sorry, the horizontal vorticity in the flow. So this is just in the vertical plane in the middle of the vortex. So you observe the dipole getting out of the screen, some maybe gravity waves here, and then the dipole is propagating like that. But the very funny features here is this very elongating stream or wake where the velocity of the flow is not zero. So the dipole is here, but it has been losing, so it's what we call the peel-off mechanism. The viscosity here, and we will show that this is the viscosity, got the effect to peel off the upper layer, and this upper layer has been left behind the flow. So what you create here, yes, is that you will create the dipole is here, but the dipole has a very funny wake in two layers that are above on each side of the vortex. And what is so this is a zoom on that effect. So this is the velocity profile at different instants. This is the picture at the late instance where the shape is like that. So you observe that the size of the pancake, so this is the vertical, and the size of the pancake diminish with time, and this is because he's leaving behind a wake, so he's losing part of his velocity by layers that has been slowed down by the viscous effect. So here there is some wake, and the interpretation of that is that you have the pancake that will start like that. While he is progressing, he's creating kind of internal boundary layers here due to viscosity, and this viscous layer is peeled off from the vortex. So the idea here is that in that flow where this buoyancy Reynolds number was very large, as we can achieve in the experiment, so it was maybe large enough, to observe the zigzag instability for the tall column dipole. In that case, we were observing this other scaling laws, that is this viscous scaling laws. So the idea would be that maybe, and I did that slice over the lunch, maybe we should do another balance in that flow, is that even if we are at very large, so there were this viscous balance that was valid when the buoyancy Reynolds number was smaller than 1, but when the buoyancy Reynolds number is larger than 1, maybe it's possible, or I will show you our evidence of that, is that there is possibility to create inner layers where the scaling of the flow will be still based on the Reynolds number. So in these inner layers, you have to change. So you take the same scaling laws for the velocity, the times, the pressure, but then you have to change the scaling law for the vertical scale. You change the scaling law for the horizontal, the vertical velocity. You change the scaling law for the density, and you obtain those equations that are nothing more than just the Prandtl equation, like a boundary layer equation. This is the same balance for the velocity, and this boundary layer equation is decoupled from the density. So the density will be forced by the fact that here the incompressibility of the flow will force some vertical velocity. So if you slow down the flow, you will force some vertical velocity, and the vertical velocity will force the density, but this equation is slave. It's not at all coupled back to the dynamics, and this set of equations is just the standard Prandtl equations for that. And the key idea here is that now, since this equation may be valid for a buoyancy Reynolds number larger than 1, if we apply this equation, we will obtain that the scale or the vertical full number of these layers selected by viscosity, by this internal viscous layer, this layer may be at a vertical full number much larger than 1. So we should observe Kelvin-Helmholtz instability even before observing this, the full creation of this layer. So this is in fact what we have observed when we did a numerical simulation of the dynamics of the dipole. So this is a dipole. Now it's a periodic box, so it's just the zigzag instability. But watch here, you have generation of very messy thing. And this messy thing, in fact, is resolved by the code because this is very high resolution. And this is due, in fact, to this creation of very, very small layers in the flow that will turn to be Kelvin-Helmholtz unstable for that. And we may show that if we look at the entropy in the flow. So the entropy in the flow is very small. So this is different Reynolds number for the same flow number. And the larger the Reynolds number, the larger the entropy creation. And when you look at the scaling of the entropy will scale like the Reynolds number, meaning that in the flow, in fact, you are generating a scale that wants to be at this viscous scale. And of course, in some of those flows, you will go through generation of Kelvin-Helmholtz instability inside this unstable boundary layer. And that we may observe that also from a cut. So if we take this evolution that you just observe rapidly because you are very fast, you observe the evolution of the dipole in that cross-section, and we may plot the density and the buoyancy, the local Richardson number, based on the local buoyancy of the flow and the local shear in the flow. And we observe that this Reynolds number will become below the value 1/4, so where it should be unstable now to Kelvin-Helmholtz instability, but for vertical shear, so horizontal billows. And after being below 1/4, it will roll up into Kelvin-Helmholtz vortices that you may observe on this field or also on the density field. So indeed, we have these dynamics where we will create very, very small layers that wants to go on the viscous scale. And this is to show you that if you plot now the Reynolds number, Freund number square, we may divide these planes. So we did different numerical simulation. And above that line, we obtained generation of Kelvin-Helmholtz instability. This was the movie you observed. Below that line, maybe I may replay that. Maybe not. Below that line, we observe the same type of evolution, but the viscous effects are too strong, or the scale is not, it's not the viscous effect. The scale we select with the viscous boundary layer is too thick, and the Richardson number is not low enough for the Kelvin-Helmholtz instability to appear in that. So my conclusion, I'm not too late, it's okay, is that if we look at the dynamics of stratified flow, there is indeed two different balance that we may do for the flow. The two balance will depend just on the buoyancy Reynolds number. So we have two regimes for the flow, and Jim and Eric has been also talking about that if you want to do a turbulence, stratified turbulence, you should be in that regime. If not, you will be just in the viscous regime for the flow. And maybe the new or not new observation is that maybe we may have over these two balance at the same time in the same flow, meaning that we may generate very small layers. And in these very small layers, we have Kelvin-Helmholtz instability. And this is also observed by Jim in different simulation. OK, thank you very much. This is for the end.
Questions? Right.
This peeling off, is that not done in the Folie Bergère? Guillotine Folie Bergère.
So I don't know. I don't want to.
Either.
Do we have any last questions? Or are we going to chop? Okay, I think we'll thank Jean-Marc again. Thank you very much. So, David, did you want to make any last comments?
Nothing but thank you all for participation and speaking. And have a safe travel back and a nice Christmas.